Hello everyone and welcome to Tutorials. Today we're gonna solve contains duplicate 2. This is actually very similar to the contains duplicate problem we have previously solved with slight differences. If you haven't seen the video on contains duplicate, I highly recommend you do so from the link in the description. Let's read the question prompt. Given an integer array nums and an integer k, return true if there are two distinct indices I and j in the array such that the number at index I is equal to the number at index j, and the absolute difference between the indices is less than or equal to k. So we need to return true if the array contains two numbers that are equal and the difference between the indices of these two numbers should be at most k. Let's have a look at some examples to better understand the question. In the first example, we are given this input array and a k value of 3. In the array, this one and this one are equal to each other, and the differences between their indices is 3, which is equal to the k value. Thus, we need to return true because the array contains duplicate according to the definition given in the question. In the third example, we are given this input array and a k value of 2. In the array, there are duplicate 1s, 2s, and 3s. However, all of them are apart from their duplicates with an index difference of 3, which is greater than 2. Therefore, we need to return false for this example. So, the brute force approach to this problem would be to try every possible combination of two numbers and check if they're equal, while also checking if their indices have a difference that is at most k. In order to do that, we need to iterate over the array once, and for each element, we need to compare it to the rest of the array. Now let's see how this algorithm works on an example. Let's say we have the following input array and a k value of 3. Now our algorithm will first consider 0 and check for the rest of the elements. Now we consider 0 to 1 and see that 1 and 0 are not equal to each other, so we advance to 2 and see that it's not also equal to 0. Now we advance to 3 and see that it's not equal to 0. Then we advance to 1 and see that it's also not equal to 0. But then we encounter a 0. Even though these two zeros are the same, their index difference is greater than 3. So we cannot return true, so we advance to 1. Now we compare 1 to the rest of the elements. First we compare 1 to 2 and see that they're not equal to each other. Then we compare 1 to 3 and see that they're not equal to each other. And finally, we compare 1 to 1 and see that they're equal to each other and their index difference is exactly 3, in which case we can immediately return true because according to the definition of the problem, the array contains a duplicate. Now let's talk about the time and space complexities of this approach. The time complexity is O of n squared and the space complexity is O of 1. This is because the comparison for each element takes linear time and we're going to be performing this for every element of the array, so we'll have two nested for loops doing linear time work. Plus, we're only using constant amount of extra space. But it turns out we can do better than that. We need to construct a fixed size window of k plus 1 elements and check if this window contains any duplicates. The reason why our window is of size k plus 1 is that if two elements have an index difference of at most k, then we need to consider k plus 1 values. If the window does not contain any duplicates, we're going to slide the window to the right, removing the leftmost number and inserting a number from the right. We will continue using this method until we reach the end of the array. In order to check if our window contains any duplicates, we're going to store the numbers in the window in a hash set and check if the newly encountered number is within the hash set. Hash set is the most convenient data structure to use here as it enables us to insert, remove, and check inclusion in constant time. And if our window contains the number, then we can immediately return true. Let's see how this algorithm works on an example. We'll use the same example array and k value as before. Here we are using two pointers where L denotes the leftmost pointer and R denotes the rightmost pointer. The left pointer marks the beginning of our window and the R pointer marks the end of our window. We're going to be sliding the right window at each step, and if the window size exceeds k plus 1 elements, we're going to shift our left pointer to the right. Now at first, our left and right pointers are going to be initialized to the 0th index, so L points to the value of 0 and R also points to the value of 0. Now since our window only contains one number and this number is not within our hash set, we'll add it to our hash set. Now we move our right pointer one place to the right, which makes it point to 1. And now our window contains two numbers, we don't need to shift our left pointer. Now we check if the value pointed by the right pointer is within our window, and we see that it's not, so we add it to our hash set. Now we shift our right pointer to the right. Now it points to this 2, and our window size is 3, which is acceptable, so we check if 2 is within our hash set, and we see that it's not, so we add it to our hash set. Now we shift our right pointer one place again, which makes it point to this 3. Now we have a window of size 4, which is the maximum size possible with a k value of 3. But in this case, we don't need to remove anything. And now we need to check if 3 is contained with our hash set, and we see that it's not, so we add it to our hash set. And we shift our right pointer to the right by one place. Now our right pointer points to 1. But now we see that our window contains 5 different values, so we need to shrink it by moving our left pointer to the right by one place. But before doing so, we need to remove the number that is pointed by our left pointer. So we remove 0 from our hash set and move our left pointer to the right by one place, which makes it point to 1. Now we'll check if our window contains the value pointed by our right pointer, and it turns out our set contains 1. In this case, we can immediately return true because we have a duplicate value according to the definition in our problem. Now let's talk about the time and space complexity of this approach. The time complexity of this approach is O of n, and the space complexity is O of k. This is because in the worst case, we visit every element in the array and store k+1 values in our hash set, which is the size of our window. Now let's see how we can code the solution. First of all, I'm going to be initializing our window as an empty hash set. And then I'm going to initialize the left pointer to the 0th index. Since we need to increment our right pointer by 1 at every step, I'm going to initialize it in a for loop. And this for loop needs to visit every element in the array. Now let's check if we have a valid window size by subtracting the pointers and comparing it to our k value. The reason why we check it like right minus left is greater than k is that the difference between the indices of two duplicate numbers should be at most k, which is why we're considering k+1 values. Now, if our window exceeds k+1 values, we need to remove the number from the left and increment our left pointer. Now, since we have a valid window, we need to now check if the number pointed by our right pointer is contained within our window. And if it is, we need to return true immediately because we have a duplicate value. And else, we need to insert this value into our window and continue. And if we don't hit this if statement until we break out of the for loop, it means that we don't have any duplicates within our array, so we need to return false in this case. And that's it. Let's hit submit. And as you can see, our solution is correct and pretty efficient. I hope you found this video helpful, and if you did so, please leave a like and subscribe. I really appreciate your support to the channel a lot, and I'll see you in the next one.